Renaissance mathematics. What was the Renaissance? A time period in which society transitioned from the Middle Ages to modernity. The word Renaissance comes from the French language meaning rebirth. Renaissance in Europe. Boyer suggests 1436 as the end of the medieval period and start of the Renaissance period, at least for mathematics history. It is the probable date of the death of Al-Kashi, a prominent Islamic mathematician at the House of Wisdom in Baghdad. And it is the date of the birth of Regiomontanus, an important European mathematician of the Renaissance. Johann Müller, or also known Regiomontanus, mathematical and astronomical prodigy. He wrote a systematic account of trigonometry on 1464. Sign tables is sexagesimal and later decimal notation, one of the earliest to have mathematical and scientific works printed. The disciplines of algebra, geometry, applied mathematics, and calculus were either born or revitalized during the Renaissance, thus leading to the modern mathematics we know today. During the Renaissance, the development of mathematics and accounting interwove. Teaching of subjects and books published was often for children of merchants, sent to reckoning schools where they learned skill useful for trade and commerce. Luca Pacioli. He was an Italian mathematician who published the influential book Summa de Arithmetica, Geometrica, Proportioni et Proportionalita in 1494, giving a summary of all the mathematics known at that time. He also investigated the golden ratio of 1.618 and so on in his 1509 book, The Divine Proportion, concluding that the number was a message from God and the source of secret knowledge about the inner beauty of things. He is famously known as the father of accounting and bookkeeping due to his tremendous contributions in the field of accounting. During the 16th and early 17th century, the equals, multiplication, division, radical, decimal, and inequality symbols were gradually introduced and standardized. The use of decimal fractions and decimal arithmetic is usually attributed to the Flemish mathematician Simon Stevin in the late 16th century. After the quadratic was solved, not much progress was made in solving equations of higher degree until the 16th century when some Italian mathematicians provided the breakthrough. Italian mathematicians of the 15th can be summarized in the names of Del Ferro, Tartaglia, Cardano, Ferrari, and Bombelli. The collective achievements of the first four was the solution of the cubic and biquadratic equations and implicitly a deeper understanding of equations in general.
Scipione del Ferro was born in Bologna in northern Italy to Floriano and Filippa Ferro. His father Floriano worked in the paper industry, which owed its existence to the invention of press in the 1450s and which probably allowed Scipione to access various work during the early stage of his life. He married and had a daughter who named Filippa after his mother. He likely studied at the University of Bologna, where he was appointed a lecturer there in arithmetic and geometry in 1496. During his last years, he also undertook commercial work. There are no surviving scripts from Del Ferro. This is in large part due to his resistance to communicating his work. Instead of publishing his ideas, he would only show them to a small, select group of friends and students. It is suspected that this is due to the practice of mathematicians at the time of publicly challenging one another. When a mathematician accepted another challenge, each mathematician needed to solve the other's problems. The loser in the challenge often lost funding or his university position. Del Ferro was fearful of being challenged and likely kept his greatest work secret so that he could use it to defend himself in the event of challenge. Despite this secrecy, he had a notebook where he recorded all his important discoveries. After his death in 1526, the notebook was inherited by his son-in-law, Annibale della Nave, who was married to Del Ferro's daughter, Filippa. Nave was also a mathematician and former student of Del Ferro's, and he replaced Del Ferro at the University of Bologna after his death.
Niccolo Fontana Tartaglia. He was a poor engineer known for designing fortifications, a surveyor of topography, and a bookkeeper in the Republic of Venice. Tartaglia's greatest legacy to mathematical history, though, occurred when he won the 1535 Bologna University mathematics competition by demonstrating a general algebraic formula for solving cubic equations. Tartaglia even encoded his solution in the form of a poem in an attempt to make it more difficult for other mathematicians to steal it.
Girolamo Cardano is an Italian physician, mathematician, and astrologer who gave the first clinical description of typhus fever and whose book Ars Magna, The Great Art, or The Rules of Algebra, is one of the cornerstones in the history of algebra. Cardano published it himself in his 1545 book, Ars Magna, along with the work of his own brilliant student, Lodovico Ferrari. In this work, Tartaglia, Cardano, and Ferrari between them demonstrated the first uses of what are now known as complex numbers, combinations of real and imaginary numbers of the type a plus bi, where I is the imaginary unit, negative. It fell to another Bologna resident, Raphael Bombelli, to explain at the end of the 1560s exactly what imaginary numbers really were and how they could be used. Although both of the younger men were acknowledged in the foreword of Cardano's book, as well as in several places within its body, Tartaglia engaged Cardano in a decade-long fight over the publication. Cardano argued that when he happened to see Scipione del Ferro's unpublished independent cubic equation solution, which was dated before Tartaglia's, he decided that his promise to Tartaglia could legitimately be broken, and he included Tartaglia's solution in his next publication, along with Ferrari's quartic solution. Are you familiar with Cardano's circles? Cardano was also the first to describe hypocycloids, the pointed plane curves generated by the trace of a fixed point on a small circle that rolls within a larger circle, and the generating circles were later named Cardano or Cardanic circles.
Lodovico Ferrari. He was an Italian mathematician who was the first to find an algebraic solution to the biquadratic or quartic equation, or an algebraic equation that contains the fourth power of the unknown quantity but no higher power. Ferrari, on seeing Tartaglia's cubic solution, had realized that he could use a similar method to solve quartic equations, or equations with terms including x raised to 4. Ferrari eventually came to understand cubic and quartic equations much better than Tartaglia's.
Raphael Bombelli. He was baptized on January 20, 1526 and died on 1572. He was an Italian mathematician born in Bologna. He is the author of treatises on algebra and is a central figure in the understanding of imaginary numbers. He was the one who finally managed to address the problem with imaginary numbers. In his 1572 book El Algebra, Bombelli solved equations using the method of Del Ferro and Tartaglia. He introduced the rhetoric that preceded the representative symbol plus and minus and described how they both work. Bombelli avoided confusions by giving a special name to square roots of negative numbers instead of just trying to deal with them as regular radicals like other mathematicians did. This made it clear that these numbers were neither positive nor negative. This kind of system avoids the confusions that Euler encountered. Bombelli had the foresight to see that imaginary numbers were crucial and necessary to solving quartic and cubic equations. At the time, people cared about complex numbers only as tools to solve practical equations. As such, Bombelli was able to get solutions using Scipione del Ferro's rule, even in the reducible case, where other mathematicians such as Cardano had given up.